Hello everybody. In this video, we're going to talk a little bit about solutions. So what is exactly a solution? So we're going to start with some kind of component that's going to be lesser than the other component. And we're going to call this the solute. Okay. This could be like a little bit of salt when you're cooking, or even like some of that instant coffee or something like that. We're going to add that to a container. And then we're going to add the solvent. And the solvent is going to be the majority of our end solution. The majority of it's going to be what we call a solvent. We add that in there. And then what happens is the solute needs to dissolve in the solvent. Okay? And it's basically going to disappear, just like salt and water, or, if you've ever made like Kool-Aid with sugar and water. And then it's going to produce a solution where the solute is completely dissolved and it's evenly dispersed throughout the bulk of the solvent, right? If I took out any little chunk of this, it's going to contain the same amount of solute as any other specific little chunk that I decided to take out. So let's look at some of our facts around solutions. Solutions are homogeneous mixtures of pure substances. The solvent is the most abundant component in a solution. The solute, and there might be more than one of them, is the less abundant component. And this is important. Where I've shown you up here an example of like a solid being dissolved in a liquid, it is not necessary for the solute or the solvent to be any particular phase. So you can talk about solutions of two gases. We can talk about solutions of gases and liquids. Any of those combinations that you could imagine are possible. And then the last thing, and this is important for your guys' homework, a solution of two solids is called an alloy. And that is most commonly seen in like metals. We talk about alloys of two different metals being combined together. So the next natural question to ask is, why do solutions occur at all? And the first way that I want to explain this through is I need to explain to you guys the idea of spontaneity. So processes get broken down into two categories. We have the non-spontaneous process, and these occur only when external energy is applied to the system. So if you just put all the components together, nothing happens unless you add extra energy into that system. But spontaneous reactions occur without the addition of external energy. So that means that if I put a solute in a solvent and they just dissolve without me having to heat it or add any extra energy, that's a spontaneous reaction. And this next step is going to go a little bit further than what our reading does, but I think that it's useful to really explain the idea behind the solution. And that is that spontaneous reactions have a negative Gibbs free energy, this delta G right here. And delta G is going to equal the change in enthalpy, which we saw in our unit on energy, minus the temperature times the change in entropy. And when this term is negative, a solution is going to form spontaneously. So, in order for this to be negative, we need this term to be negative, and we need this T delta S term to be negative. Or we need to have this one be more negative than this one is positive, or this one to be more negative than this one is positive. In this difference here, we need to get a net negative thing. So when delta H is negative, it's going to favor forming a solution. And that's going to occur when we have an exothermic process and energy gets released during the process. And we're going to have a positive delta S, which is going to make this whole term negative, when we have a less ordered system. Okay, so we want a more chaotic system, and that's going to favor solution formation. So let's dig a little deeper into that enthalpy term. Before we have a mixture, we have just the solute as a pure substance all by itself. The only interactions are between one solute component and another solute component. And similarly, on the solvent side, the solvent can only interact with other solvents. And we've seen different kinds of intermolecular forces so far when we were talking about that in the unit about intermolecular forces. But what happens when we finally add the solute to the solvent is we introduce a new interaction between a solute and the solvent. And what basically winds up happening is that when this solute-solvent interaction is stronger than the solvent-solvent interactions or the solute-solute interactions, then the solute is going to preferentially interact with the solvent, and that's going to favor the formation of a solution. Mathematically, that means that this delta H term, because each one of these has an associated enthalpy with it, is going to be less than the sum of the solute interactions and the solvent interactions. This is what leads to an exothermic reaction where energy is released during the process of dissolution and the formation of a solution. And it means that solvation, the act of forming a solution, is favored. And similarly, if the interaction between the solute and the solvent is not as powerful as the solute-solute interaction or the solvent-solvent interaction, well, this solute is just going to continue to prefer to interact with other solutes, and the solvent's just going to continue to prefer to interact with other solvent, and then the solvation process is not favored. Now, it can be true that this could occur if the other term, the T delta S, is so negative, the negative T delta S term is so negative that it overcomes this. But sometimes this could hinder the formation of a solution altogether. So now let's talk a little bit about entropy. And the first question is, so what is entropy? It's really a pretty confusing topic that isn't really described well in texts at this level. So many texts refer to entropy as a degree of chaos present within a system. But it's really better defined as the tendency of a system towards a stochastic ensemble. Stochastic means random, and an ensemble is like a population that can be sampled statistically. But, I mean, what does that even mean? Okay. But really, we see the process of entropy all the time, and it's so ubiquitous that we really don't think much about it. Okay? And really what entropy does is it drives everything to just kind of spread out and become kind of even all over the place, right? So here I want you to picture that you have a warm metal rod. It is never going to spontaneously happen that that metal rod just becomes cold at one side and hot on another. All the heat in that rod is never just going to move to one side of it. Okay, but if you did have a metal rod and it was cold and you heated up one side, it will spontaneously spread throughout the rod to create a more even heat throughout the entire thing. And that is the process of entropy. Things tend to just kind of spread out and become even throughout the system that they occupy. Another example would be one with a flower that you can smell, right? At first, all of the scent of the flower is focused right around it, but it eventually just spreads out until it fills the volume that you're in and you can smell it, right? What never does happen, though, is that the scent of that flower just spontaneously goes back to the flower and stays there and never spreads out, right? So that's kind of the idea behind entropy. It's that the system will always reach some sort of random statistical model where everything kind of spreads out and gets nice and even. It is also true that the entropy of the universe always increases. So if you are an astute student, you may have said to yourself, but that doesn't seem quite right. The entropy of the universe can't always increase because I can create a more ordered system. I can go and fold all my socks and stack them in neat little piles and stuff. And so what is actually true is that we have this sort of system here where we're going to make a distinction between a system and the surroundings, and together the system and its surroundings comprise the entire universe. And what's happening when you fold your socks is, yes, you're decreasing the entropy of the system, but that only comes at the cost of increasing the entropy of the surroundings. And that cost isn't always obvious, like in the example where you're folding socks, right? What really happened when you folded those socks is that you increased the amount of chaos in the system just by basically being alive and expending energy, right? You blew off a whole bunch of CO2. You broke down a bunch of really ordered molecules in the form of food. And you're creating a more chaotic system in general throughout the entire universe by ordering your system. On the molecular level, we can look at it like this. So whenever we take a random sampling of molecules and we give them a regular order, we bring them closer together, we've created order. When we have attraction between those molecules, we get a negative enthalpy term because we've increased the attractive intermolecular forces. We've decreased the entropy of the system, but at a cost, we created an even more chaotic surroundings, right, than what we were able to do when we ordered that system. And then in this whole scheme of things here, what winds up happening is that it is this delta H term that allowed this to happen. That by increasing the intermolecular forces, we were able to overcome the fact that we created a more ordered system. So let's take a look at a special case where we're going to form solutions by taking a solid solute and dissolving it in a liquid solvent. So in this case, this forming solutions always result in a positive delta S, and that's because solids are very ordered systems, and once you put it into the liquid and allow it to spread out and interact less with one another, it creates a certain level of chaos, because those molecules when they were in the solid couldn't move around, but now that they're in the liquid, they're actually able to gain some mobility and move around within the bulk of the solvent. So because we always have a positive delta S that's going to favor the formation of a solution, it is actually up to the enthalpy term and the solute-solvent interactions to determine whether or not that actually winds up forming. So when we have attractive forces between the solute and solvent, then our delta H term is going to be negative. As we said, the negative T delta S term is always going to be negative. That means that delta G is negative, and we have a spontaneous reaction. So that makes a lot of sense. When the solute likes the solvent and they want to interact with one another, the solution actually forms. If we have a different situation where the solute and solvent are repulsive to one another, well, the delta H term is positive. It's working against the formation of solution. The entropy term, negative T delta S, is still going to be negative. So now it depends on how repulsive this is. Okay? So if it's so repulsive, or if it's not repulsive enough to overcome the negative T delta S term, then delta G is still negative, and it still have a formation of a solution. However, should the repulsion be so strong that it overcomes the entropy term, then delta G becomes positive and a solution does not form. Now, because this negative T delta S term is favoring a solution forming in this case, increasing the temperature is going to increase this term, and that's going to favor the formation of a solution. Okay, so the moral of that story is that even if you got into a situation where this repulsion is overcoming the entropy term and making it so a solution doesn't form, you might be able to get it to form by increasing the temperature in this circumstance, by increasing this negative T delta S term. Now let's look at the case where we have gases and liquids. So this is in many ways the opposite of the solids and liquids case. So in this case, solutions always result in a negative delta S because gases are very unordered systems. And when you put it in the liquid, you now confine it to a finite amount of volume, right? Gases can spread out as much as they want, but you're ordering it when you dissolve it into a liquid. And this is kind of difficult for people to picture sometimes, a gas being in a liquid, but really this is happening all the time. This is the fizziness that's inside of a soda. It is that kind of gross rotten egg smell maybe you've smelled from water before. That's hydrogen sulfide, which is a gas that's dissolved in the water. There are many, many cases where gases are actually dissolved in liquids. And they always have this negative delta S because you're now confining and ordering that system more. So because the entropy doesn't favor the formation of solution formation only occurs when there are significant attractive solute-solvent interactions. Okay, so it's got to overcome that entropy term in order to get a very negative enthalpy term that's going to favor the formation of solution. And also because entropy is not favoring the formation of solution here, increasing the temperature is actually going to make it so that it's even less favorable. So in this case, decreasing the temperature is going to lower the value of the T delta S term and favor the solution formation, which is pretty intuitive actually if you think about it. Something like a soda. If you let it get warm, it gets flat, and that's all of the gases that have been released from the solution. But if you put it in the fridge and keep it cool, it stays really nice and fizzy. So now I want to introduce a little bit of nomenclature, a new term for us called the ideal solutions. So ideal solutions are ones where the solvent-solvent, solvent-solute, and solute-solute interactions are all roughly the same. So basically our delta H term in this case is essentially 0. In that case, solvation is driven by entropy alone, right? Because that's the only term that could be negative to give us a negative Gibbs free energy. Ideal solutions are usually formed from structurally similar pure compounds. So it makes sense that if the solute is like the solvent, then the solute-solvent interactions are going to be similar to the solute-solute interactions or the solvent-solvent interactions. If everything's the same, then all the interactions should be roughly equal to each other. Some examples of compounds likely to form ideal solutions are hydrocarbons with hydrocarbons. A hydrocarbon, we've actually seen this already. This is a compound that is made out of just hydrogen and carbon. Examples of this would be like methane, propane, butane, hexanes, which is a common solvent we use in chemistry. A lot of different organic compounds are going to be hydrocarbons. This is the same stuff that's inside of your gasoline and whatnot too. Alcohols with other alcohols. So there are different kinds of alcohols. We can have methanol. We can have ethanol, which is a typical alcohol that's like a beverage. Isopropanol we've seen is like rubbing alcohol and stuff. So if you have two different kinds of alcohols, they're going to tend to form ideal solutions. And then maybe like a noble gas with another one of the noble gases. They hardly interact with each other at all. It's pretty easy to have ones that have pretty different properties, but still are going to form an ideal solution when you're talking about noble gases. Okay, let's talk a little bit more about the process of dissolution. So this is dissolving one thing in another. There are 3 things that can be done to speed up dissolution. The first thing that we can do is increase the solvent-solute surface area. So dissolution is going to happen at the interface between the solvent and the solute. If you make that interface bigger by, say, grinding up a solid so that it has more surface space exposed to the solvent, or say adding solvent, or by thoroughly mixing it so that the solvent is kind of constantly moving over our solutes, you're going to be able to get better dissolution that happens a little bit more rapidly. You can add or remove energy. So if we've seen some dissolution is going to be favored by the addition of energy, i.e. heat. Some of them are going to be favored by the removal of energy. So here we have our solids, and we typically are going to heat those, and we're going to mix them, which is actually another form of energy that we're adding. We're adding kinetic energy to it. And in cases where we're going to make solutions of gases and liquids, we're going to cool them. And the third one is going to be time. It will always take time for the solvation process to come to equilibrium. And what I mean by equilibrium is we're going to reach a point where we've saturated the solution and we can't add any more, but it's going to take time for that to happen. I will also mention that the amount that you can dissolve one thing in another is really only dependent upon the temperature of the overall solution. All these things are just going to affect the kinetics of the situation. They're just going to speed up the process. They can't actually make it so that you can dissolve more of a thing in anything else. That's only really the temperature dependent. So there's a connection between polarity that we saw before, meaning that it has a dipole moment. the molecules do that makes them polar, having polarity. That's how we talk about it in the bulk solvent term, and solvation. So solutes tend to be soluble in solvents with similar polarities, meaning that the dipole moments of the solutes are similar to the dipole moments of the solutes or the solvents. And it's also true that solute-solvent pairs with similar polarity, i.e. again, similar dipole moments, are more likely to form ideal solutions.